This is the second part of our 7.1 What is a Sampling Distribution notes. We're going to start with sampling variability here. It says, how can X bar be an accurate estimate of mu? In other words, how can our sample mean be an accurate estimate of what the population mean might be? It says, after all, different random samples would produce different values of X bar. Basically, if you took different random samples, you would probably get different sample means for those samples. This basic fact is called sampling variability. And in the blank there, the value of a statistic varies in repeated random samples. Which means if we do a bunch of different samples, the sample means that we get from each one of these samples is going to be a little bit different from the next. So to make sense of that, well, all the sample means might be a little bit different from one another. We're going to take many samples. How many? Well, a lot. Let's just say we're going to take as many samples as we can possibly take from the population and calculate the sample mean, for example. So what is sampling variability? Why do we care? So we know that individual observations, like just individual people that we sample, right, their observations are going to vary. Well, that means our samples together will vary. So to put that in context, if I'm observing the mean height of a student at Lake Park, we know that individual people are going to be different heights. Therefore, whatever random sample I do, we could see different average heights for each sample. So why do we care? Well, we need some way to estimate the variability. The variability of what? What do we want to estimate here? We want to estimate the variability to know how close we are to the true population parameter. So I know that all the sample mean heights I get from my random sample of Lake Park kids, they might be a little bit different than one another. But I want to study that variability so I can know how close my sample means are getting to the actual true population parameter. So in the case of height, it's not difficult to imagine. If you do a random sample and I do a different random sample, we might get different means within our samples. Who's going to be closer to the true population mean? Well, it's difficult to say. But that's what we're trying to understand. And it seems possible that it'd be hard to get it exactly correct. If I do a random sample, whatever that mean height is, it might be hard to get it exactly correct in terms of what the true mean height is for a Lake Park student. So I'm probably going to be off by just a little bit. And if you've seen any political polls, that amount that you're off by, that's called the margin of error. Whether you're above or below, this idea of variability, we allow for some margin of error. That's the plus minus thing. All right, let's take a look at example 3 here. It says reaching for chips. A population of 200 red and blue chips has been prepared. The parameter is the actual proportion, P, of red chips in the population. And so we know that half the chips are red. So we're going to investigate this idea of sampling variability by taking 30 random samples. You can imagine one for each kid in the class. And then each kid gives their proportion of red chips that they observed. So 30 random samples of size 20 from this population of 200 chips. And then you could imagine this as being a class dot plot where each kid comes up and marks the sample proportion of red chips that they got. So it shouldn't be surprising that a lot of kids got 0.5 because apparently there's truly half the chips as red in the population. But part A asks about this dot that might be a little bit more surprising. It says there is one dot at point 2. Explain what this value represents. And this is a really common question for this chapter. So we just need to be careful in identifying what that really means, what this graph really represents. So you could think about this as being maybe a class dot plot, right? So each one is some kid's result. They took a random sample of 20 chips, and that was the proportion of reds that they got. So let's be clear about that. The 0.2 dot, that means that in an SRS of 20 chips, so some kid does an SRS of 20 chips, there were actually 4 red chips. How do we know there was 4 red chips? Well, if the proportion's 0.2 and they drew 20 chips out of the bag, that's how they got p hat to be 0.2, right? 4 out of 20. So just to be really clear about that, that's the result of one of these SRSs, right? There was 30 overall, but this is just one of them. So in an SRS of size 20, there were 4 red chips. That's exactly what the dot at 0.2 represents. And then part B says, describe the distribution in context. And that's a question straight from chapter 1. So if you can think about a dot plot, chapter 1, we had an acronym for it, right? That acronym was SOX. So we need to mention something about the shape, the outliers, the center, and the spread. And we can do this in one sentence. Let's just make sure to use context. So let's start with the distribution of, and what are these things, right? So this is where that context piece comes into play. These are actually sample proportions. So the distribution of sample proportions of red chips. There we go. Context, points, check. And let's start with the shape. So it looks, I would say, it's got the bell shape going. I would say roughly symmetric. You could start to make an argument for left skew because of that guy, but I think it's more so symmetric. So we could say it's roughly symmetric. Boom. So now we put a check for the shape. Definitely centered at about 0.5. Right? So I'm just going to say centered at 0.5. So now center's good. Check mark on the C. So I got shape, I got center. The spread, we could say it ranges from 0.2 to 0.7. So we've covered the spread. Check mark on the S. And we have one possible outlier, it looks like, at 0.2. So that's a really important piece. If you're going to say there's a possible outlier, you have to point out where it is. So we're referring to the one at 0.2. And there it is. Full credit. We mentioned shape, outliers, center, and spread, and we did it in context as well. All right, and now the interesting part here. Part C says, would it be surprising to get a sample proportion of 0.85 or higher in an SRS of size 20 when P is truly 0.5? Justify your answer. Well, each one of these little dots represents an SRS of size 20. And you'll notice we didn't get anything near 0.85 here. So would you be surprised if one of the students said, oh yeah, I got 0.85 for my result? And I think judging by this graph, we would definitely be surprised and want to check that person's work if they said they got 0.85, because the highest we observed here was 0.7. So would you be surprised if 0.85 or higher showed up? So that would be, there's 0.85. And you'll notice we don't even have anything close to this line, let alone above it. So yes, we would be very surprised. So a sample proportion of 0.85 or higher would be very surprising in this case. Why is that? Just based on this simulation, right? This is the evidence we're talking about. So yes, we'd be very surprised to see something 0.85 or higher. Why is that? Well, in 30 random samples here, the highest proportion we saw, the highest p hat observed, was only 0.7. All right, so we're not even coming close to 0.85. So yeah, we'd be very surprised to actually see 0.85 in this case. Okay, and then part D says, suppose your teacher prepares a bag with 200 chips and claims that half of them are red. So similar to the problem above, teacher gets together 200 chips and makes the claim that half of them are red. A classmate takes an SRS of 20 chips, 17 of them are red. What would you conclude about the teacher's claim? Explain. So the student got 17 out of the 20 to be red in the sample SRS. What would you say about the teacher's claim? Because right now the teacher's claiming that the bag is exactly like the one from above, that half of them are red and there's 200 chips total. But if you look at what this kid's results were, p hat would be 17 out of 20 for this kid, which is exactly 0.85. So if this kid actually drew 17 out of 20 being red, and we saw a sample proportion p hat of 0.85, well, does that support the teacher's claim, or does that go against the teacher's claim? Well, that definitely goes against the teacher's claim. That's strong evidence against the teacher's claim. The teacher's claim was that it was 50-50, so there was half red. But if it were half red, we would expect the chances to model something like this. And we already said that for this distribution, 0.85 or higher, very unrealistic. And this one was truly 50-50, red and blue. So for this example, we don't know what the teacher loaded the bag with, but if a kid got 0.85, right, your classmate pulls 17 out of 20 to be red, right away that gives us cause for concern. We don't think it's actually 50-50. And why are we making that claim? Well, we already mentioned in Part C, a sample proportion of 0.85 or higher would be extremely unlikely if the true population proportion was actually p equals 0.5. So we showed that in Part C. Based on that simulation, it was extremely rare to see something 0.85 or higher. So if we have another case where the teacher says the bag's loaded up with 200 chips and half of them are red, but then we have a kid that pulls 17 out of 20, right away that gives us cause for concern. Maybe the teacher didn't count them out right. All right, so let's move on to the diagrams on the next page. The first part here says if we took every one of the possible samples of size n from a population, calculated the sample proportion for each, and graphed all of those values, we'd have ourselves a sampling distribution. So we can continue with that model of the chips, the red and blue chips for this idea. So in green here, this is the definition of a sampling distribution. It says the sampling distribution of a statistic is the distribution of values taken by the statistic, which could be, sample mean, sample proportion, in all possible samples of the same size from the same population. It basically just reiterates what this italics quote says. But here's the deal. That's okay. I mean, that's easy to understand in theory if you took every single possible sample. But in practice, that's virtually impossible to do, right? So it says it's difficult to take all possible samples of size n. So what do we do to account for that? Well, we can take a bunch of them by just running a simulation, right? So a simulation will give us many, many samples. So that's how we obtain our sampling distribution if we conduct a simulation. And so in that way, we can simulate, maybe not exactly every single possible, but we can simulate almost the majority of every possible sample. So what's going on with the diagram here? And the same thing with the chips, half blue chips, half red chips, right? There's 100 of each. So distributions of sample data. If we go to the next level, this would be like kids in the class, each person doing an SRS of size 20, right? So they're randomly drawing out 20 chips with replacement, and the results might look something like this. So here's this kid, and then there's a whole bunch of kids, so you just have ... all the way down to the last kid, right? So everybody does a simulation, and they all get a different p-hat. Like this kid had 8 out of 20 red, this kid had 11 out of 20 red, this kid had 13 out of 20 red, all the different possibilities, right? And we do that many, many times, right? Each kid does it over and over and over. And for each kid, we can plot their p-hats. So you can think about this as being a dot plot over here with a bunch of dots. Each kid put down their results for p hat. And it shouldn't surprise you that if the true proportion of red was 0.5, that this distribution is centered right over that value of 0.5. So that's our way to simulate all the possible samples of size 20 and then record the proportion of red chips. We do it over and over and over and over and over, and we try to simulate all the possible values. Now, I don't think we got quite all of them, right? But we got virtually all of them, and that makes this distribution. Notice it's symmetric, and it's centered right where we would expect it to be. If the true proportion of chips was red, then we do this sample many, many times, most likely to get 0.5 here. So this really illustrates the idea of a sampling distribution. You have our population distribution. You take a bunch of individual samples, right? So each one of these is how each kid's individual sample was distributed. Like, oh, my sample, I got 12 blues and 8 reds. Great job. That's your sample distribution. And we do that many times. We get all those samples. We put it together. That forms our sampling distribution. And this idea lays the foundation for a lot of things we'll do in statistics. Let's go to the next piece here. It says, what is a sampling distribution in general? Can we summarize it? And why do we care? So I color-coded this, right? What is a sampling distribution? We just saw an example of one. It actually illustrates, and by that I mean it graphs or displays all the possible values of a sample statistic. And what the heck's a sample statistic? Well, that could be our sample means, or like we just saw with the chips example, that could be our p-hats, or standard deviations, whatever that is. It tries to show all the possible values for a sample statistic. And not only does it show all those possible values on the x-axis, but when you start stacking up dots, it shows how often they occur in a dot plot, for example. So it shows all the possible values and how often those values occur. And why do we care so much, right? I said it was an important piece for statistics. Well, in general, we need to know what counts as usual versus unusual. Like how we answered the question about the teacher's red chip example earlier, right? We said, I don't know, that's too unusual, that's too rare to happen by chance because I have a simulated sampling distribution. So that's why we need to know, and that's why we care. What counts as a typical result, and then what stuff is too rare to make us start to become suspicious. Okay, and the last piece here, I've definitely seen this on some AP Stats questions. Can you differentiate between these three ideas? What's the distribution of the population? What's the distribution of the sample? And then what is the sampling distribution of a sample statistic? So we've got to be able to define all three separately. We've got to know what each one means on their own. So I'm going to color code again. For the population, I use blue, right? The distribution of the population, that would be like if we had data for every single member or every value of the entire population, right? So if we were able to graph every single person or member of the population, that's what the distribution of the population would do. In most practical examples, we don't have information about every single person in the population, right? But you can imagine if we did. So for example, if we had data for every student at LP, right? So if we had data on every student, we wouldn't have to do a random sample or a random survey of LP students because we would already know the data about every single one. So the entire population, that's the distribution. What about the parameters that go with population? Remember, we have population parameters. So in blue here, we could have the population mean, mu, population standard deviation, sigma, the true population proportion, which is just p. It's a lowercase p, by the way. And then we saw before, capital N, that was the size of the population. So population parameters, those are there to describe characteristics about the distribution of our population. Okay, so we know what the population is. We know what it does if we actually graph the distribution. How about the distribution of the sample? So the sample implies kind of singular. So in red here, well, the distribution of the sample, we could say displays the values observed during a single sample. Like when I was pointing out individual kids with the chips example earlier, I got 12 blue chips, I got 8 red chips. Great job. So that was the distribution of your individual sample. For example, if I have 8 coin flips, my result might be just for my individual sample, right? Heads, heads, tails, heads, tails, 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 heads. So distribution of the sample would just be one individual sample and how that looks. All right, so what are the symbols that go with samples? Remember, it's sample statistic. So X bar, S, P hat, or N, right? So we have sample mean, sample standard deviation, sample proportion, or lowercase n was number, or we could just say size of the sample. So far we've got distribution of the population and distribution of the sample. And if we think back to our diagram here, that's exactly what these two would be. Here's our population distribution, so that's all the red chips, there was 100, and all the blue chips, there was 100. And then distribution of the sample would be just one kid's individual sample. And then that was repeated many, many times. And then the last piece that we're going to get to is the sampling distribution. So the sampling distribution of a sample statistic, what does that do? Well, we've actually covered it already. That displays all possible values of a sample statistic. So if we could have possibly taken all possible samples of size 20 from the chips and recorded the p hat, the sample proportion of red chips for each one, that would give us our sampling distribution. So let's use that for our example. How do we simulate a sampling distribution? Well, we get a bunch of data, so we can do a class graph, one for each student, to show all of the simulated p hats, just like the example with the chips above. And then if I could draw with the notation, I would probably draw a dot plot, but instead of dots, I would use a sample statistic. For example, X bars or p hats. So that would be a sampling distribution, all the possible sample means or sample proportions that we could make. All right, so we've talked about what is a sampling distribution exactly, and then we made this distinction right here between these three, and that's huge. So that is all for these notes. I'll see you in class.